So starting chapter 2, section 2.1 is about describing location in a distribution. So we are going to learn about percentiles, standardized scores or z-scores, and then we're going to use those percentiles and z-scores to compare the location of different distributions. So here are the scores of all 25 students in Coach Brooks' third period statistics class on their first test. The bold score is Jenny's 86. How did she perform on this test relative to her classmates? So what we'll do is we'll take this data and we'll make a dot plot. So the dot plot displays the class's test scores and Jenny's score marked in red. So I know it's not red on your paper, but if you look right here, 86 is just barely above the 85. So that's Jenny. So from the dot plot, we can see that Jenny's score is above the mean. It's above the balance point. If I think about where this graph would balance, it would probably balance right about there. If I think about those dots balancing. And so we can see she's above the mean. We can also see that she did better on the test than most of the students in the class. There were only 3 students that did better than her. So one way that we can describe Jenny's location within this distribution is something called a percentile. So we can describe Jenny's location by describing what her percentile is in this distribution. So recall that the 3 quartiles, so quartile 1, so that goes from here to here, that's quartile 1, is that cutoff, and that's that first 25% of the data. And then we had our median, that's the middle, and then we had quartile 3, that's the top of the box here, and then we had our maximum. But remember that each of these sections is worth 25% of the data. There's 25% in each of these sections. So our quartiles cut our data into 4 roughly equivalent sizes. That's very similar to what a percentile is going to do. A percentile is going to cut the distribution into percentages of basically 1% sections, and we're going to have 100%. Okay, so basically each one of these little sections is 1%, and we'll be able to quickly see what percent of each of the distribution is someone at. Okay, so this is another kind of a visual here. A percentile, this is going to kind of give you a visual of where different percentiles might be. So like the 50th percentile is obviously in the middle, and then we've got our 20th percentile would be at the, so we've got like 10, 20, 30, 40, 50, 60, 70, 80, 90, and then you can see we've got, all the different percentiles, okay? So what is a percentile? A percentile is the percent of values in a distribution that are less than the individual's data value. So if I have somebody that is right here in the distribution, then they would be at the 20th percentile, meaning that there's 20% of the data less than they are, than what their value is. Someone at the 50th percentile, that means that there's 50% of the graph that's less than that data value. The 82nd percentile means that there's 82% of the data less than what they are, and so on and so forth. Okay, so a percentile is the percent that is less than an individual's data value. So using that dot plot, we can see Jenny's 86 places her 4th from the top of the class. Okay, so she's got the 4th highest score. So because there are 21 of the 25 data values that are less than her score, then I can do 21 divided by 25, and that gives me 84. So that puts Jenny at the 84th percentile because 84% of the class did less than Jenny. All right, 84% of the class was less than Jenny's. Now be a little bit careful with your language here, because with a percentile, we always want to talk about that we are at the 84th percentile, okay? We don't want to say that we're in the 84th percentile because if you look here, Jenny's not in the percentage that is less than her. She's greater than that. So she's at the 84th percentile. It's a slight little, nuance that we need to be careful about. All right, so again, looking at this same distribution, let's do a couple of examples. Refer to the dot plot of scores on Coach Brooks' first statistics test. Find the percentile for Paxson, who scored a 72. So 72 would be right there, okay? So Paxson scored the second lowest score in the class. So there is only one value that is less than Paxson's score, okay? And so there's only one out of the 25 tests that were scored that are less than Paxson. So 1 out of 25 is 0.04. So that means that Paxson is at the 4th percentile. Now, Reagan's test score is at the 48th percentile of the distribution. First thing we're going to do is interpret this value. So here's what that means. That means that Reagan got a score that was better than 48% of all grades. So Reagan scored better than 48%. So basically what we need to figure out is how many values are there that would be less than Reagan's. And so if I found out what 48% of the number of students, 25, 48% of 25 would tell me how many numbers are less than Reagan. So 48% of 25 equals 12. So that means Reagan did better than 12 students. So if I just start counting from the bottom here, then that'll tell me where Reagan's at. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means Reagan is the very next number, which would be an 80. She's one of those two 80s. It doesn't matter which one, but Reagan scored an 80. So what score did Reagan earn? She got an 80. And that's because there were 12 values that she did better than. Alrighty. Now, the median of a distribution is roughly the 50th percentile. For instance, 80 is the median score of Coach Brooks's first test. As you saw in the previous example, Reagan, who got an 80, that put her at the 48th percentile of the distribution. And so that's about 50%, okay? So it is an estimate. The first quartile, Q1, is roughly the 25th percentile of the distribution. So wherever that is, so if I look at what's the lower 25%, then I can see kind of where the Q1 would be, and that would be the 25th percentile. The 75th percentile is quartile 3, and that's going to be where roughly 75% of the data is going to be less than that number. Now, one thing we want to be very careful about is our context of our problem. So, for example, if we're talking about test scores, then obviously you want to have a high test score. You want to have a high percent below you. You want to be up at the top. But a high percentile is not always a good thing. So here's an example. A student whose number of absences is at the 90th percentile would probably be in danger of truancy or losing credit for a class. That's because they have the number of absences that they have is more than 90% of other students. So they have a lot of absences. So just be careful with context. A challenge here for you. is, can you think of a quantitative variable where it would be preferable to have a low percentile? So when would you want maybe your percentile to be 5% or 10% or something like that? Usually that's going to be something where it's where the what you're looking at is like something that's negative or a bad thing. Okay, so or I'm sorry, something that is a good thing. That's what I meant to say. So for example, if you are in the 10th percentile for the number of speeding tickets that you've gotten, right? So only 10% of people have gotten less speeding tickets than you. Well, that's good. That means you've done a good job. You want to have a low percentile if it's something that is a negative. All right. Describing location in a distribution. So a percentile is one way to describe that location, but a standardized score or a z-score is another way. So what is a standardized score? A standardized score, or a z-score as we like to call it, for an individual value in a distribution tells us how many standard deviations from the mean the value falls, and in what direction. So to find the z-score, we're going to use a formula. Here's the formula right here. Our z-score is going to be, we're going to take the value from that distribution, and we're going to subtract the mean. Then we're going to divide by the standard deviation. Whatever number we get, that is our z-score. That is the number of standard deviations that we had to use to get from the mean to the actual value in the distribution. So let's look at a little example here. The table provides numerical summaries for the data from Coach Brooks's first statistics test. The dot plot displays the data, and Jenny's score is marked in red. Again, it's the same score. It's not on your paper in red, but there it is. And so here's our summary statistics. Where does Jenny fall within the distribution? Basically, like, what is her standardized z-score? So if we take her value in the distribution, which is 86, and we subtract her mean of the distribution, and so if I look here at the chart, I can see the mean of the distribution is 80. So if I take her value of 86 and I subtract 80, and then I divide by the standard deviation, which is 6.07, whenever I do that calculation, I get 0.99. So what does that mean? That means Jenny's score is 0.99 standard deviations above the mean. That's almost a full standard deviation. So again, if I look here at my mean was 80, if I added a standard deviation of about 6, then I would get an 86, which is exactly what Jenny scored. And so the only reason that this is 0.99 of a standard deviation is because the actual standard deviation was 6.07. And so when I actually add a full standard deviation, then that would mean she would have to get an 86.07, okay, which we know she can't get. So that's why the z-score is 0.99 instead of the full 1. Alrighty. Now, z-scores, the thing about z-scores is if you get a z-score that is equal to 0, that means that your value was exactly equivalent to the mean of the distribution. And the reason that that is if I take 80 and subtract 80, for example, let's say somebody got an 80 on the score on the test. If I take 80 and subtract 80, I get 0. And so whenever I divide by that standard deviation, I still have a 0. And so the z-score of that distribution, or of that person's score, would be a 0. If I get if I get a positive number, that means that the value was above average, and it tells us how many z-scores, or how many, it tells us how many standard deviations above the mean they scored, similar to Jenny. Jenny was almost one full standard deviation above average. And so for large z-scores that are positive, that means that we were above average. Z-scores that are positive means that we're above average. The bigger the number, the further above average we were. And then, of course, if we have a negative z-score, then that means that we had a value that was below average. So that means when we did our value minus mean, we get a negative number, and so that gives us a negative z-score. All right, we're going to do another example here. We're going to find the z-score for Jacob. Jacob scored a 67 on Coach Brooks's first test, and then we're going to interpret his z-score. So Jacob is right here. He got the lowest score in the class, and so we're going to find and interpret his z-score. So z equals value minus mean divided by standard deviation. And so we're going to take his value of 67. We're going to subtract the mean of this distribution, and we're going to divide by the standard deviation of this distribution. And we get negative 2.14. So that negative tells us that Jacob was below the mean. Remember, the mean is 80. And so we can see, obviously, that Jacob is below the mean. And not only do we know he was below the mean, but we know that he was 2.14 standard deviations below the mean. So Jacob's score was 2.14 standard deviations below the mean. And the reason that we're saying below is because it was negative. All right, so what are z-scores and percentiles good for? The biggest thing that they're good for is that they are going to tell us, or they're going to give us a way that we can compare things, okay? And so we want to compare distributions that are maybe not the same. For example, Marty had a standing long jump of 71 inches, and he did 39 sit-ups. So those are two very different things. Which performance was better relative to other students who participated? So if we look at the long jump distance, or in inches, number of sit-ups is just a number, a counting, and so we can't really compare them directly. I mean, 71 inches is definitely, seems like it would be a pretty long jump, but, is that better than 39 sit-ups? Well, I'm really not sure. It just depends on how that is within relation to the other students. So if we look at this, we can find that Marty's 71 inches that he did his long jump, that was at the 75th percentile. Now, obviously, I would have to know some other information in order to have calculated that, but they're just telling us that his 71 inches was at the 75th percentile. So that means that Marty did better than 75% of the other kids on the long jump. And then it tells us that his 39 was at the 50th percentile for the distribution of sit-ups. So that means he only did better than 50% of the other students on the sit-ups. So that means that he did better in the standing long jump than he did on, relative to others, than he did on the sit-ups. He was 75 percentile, so there were 75% of students that did worse than he did on the long jump, and he only did better than 50% on the sit-ups. So he did better on the standing long jump in relation to other students. So let's look at another example here. This is an example between Miss Lakey and Coach Brooks and the heights that they were when they were younger. So we're going to see who was taller when they were younger, relatively speaking. So Miss Lakey was 55 inches tall at age 9. The distribution of heights for 9-year-old girls has a mean of 52.5 inches and a standard deviation of 2.5 inches. Coach Brooks was 58 inches tall at age 11. The distribution of heights for 11-year-old boys has a mean of 56.5 and a standard deviation of 3. Who is taller relative to other children of their gender and age, Miss Lakey or Coach Brooks? So anytime you see relative to others or relative to each other, we're going to want to find a z-score. So remember, z equals value minus mean divided by standard deviation. So Miss Lakey's value in her distribution was 55. That's how tall she was at age 9. That distribution has a mean of 52.5. We can already see that she was above average, but now we're going to divide by the standard deviation to see what her actual z-score is. So the z-score for Miss Lakey would be 55 minus 52.5 divided by 2.5, which is 1. So that means that Miss Lakey was 1 full standard deviation above average. For Coach Brooks, we're going to take his value of 58, subtract the mean of 56.5. Now we can already see Coach Brooks was also taller than average, but we're going to divide by his standard deviation of 3. And this is going to give us Coach Brooks' z-score. So the z-score for Coach Brooks is 0.5. So what that tells us right here is that Miss Lakey was taller relative to others at age 9 than Coach Brooks was at age 11. So relatively speaking, Miss Lakey was taller than Coach Brooks within these particular distributions. All right, let's look at our example problem. The U.S. House of Representatives has 435 voting members. Each state is allocated a number of seats in the House based on its population when the census is taken every 10 years. A dot plot of the number of representatives from each of the 50 states in 2019 is shown, along with summary statistics. The red point on the graph is the state of Ohio, with its 16 representatives. So here's Ohio right here. Find the percentile for Ohio and interpret this value. So remember, for percentile, what that means is that it's whatever percent is less than that value. So basically, I just need to count up how many numbers are less than Ohio and find out what that is out of the total, which is 50. So if I count these, there are 43 of these dots. So 43 out of 50 is 0.86. So that means that Ohio has more representatives than 86% of all states. So that is what that percentile means. Now it says that South Carolina is at the 52nd percentile of the distribution, and we have to find out how many representatives did South Carolina have. So if South Carolina did better than 52% of the states, then we're going to find out what is 52% of 50. And when I find that out, that gives me 26. So that means South Carolina was just better than 26 of the states. So I'm going to just count the bottom 26. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So that means South Carolina is right here. So it looks like that's going to be at 7. Okay, looks like these are by ones. So that looks like South Carolina had 7 representatives. Okay, so South Carolina had 7 representatives. All right, now we're going to calculate a standardized score for Ohio. So that's going to be our z-score. It's the value minus the mean divided by the standard deviation. And so Ohio's value we found, we saw earlier was 16. Okay, Ohio has 16 representatives. We're going to subtract the mean of this distribution, which is 8.7. And then we're going to divide by the standard deviation, which is 9.723. And that gives us 0.751. So what that means is Ohio is 0.751 standard units or standard deviations above the mean. Ohio is 0.751 standard deviations above the mean. All right, and the last question says, the U.S. House of Representatives has 435 voting members. Each state is allocated a number of seats in the House based on its population when the census is taken every 10 years. How many counties does each state have? The table displays summary statistics for these data. So again, we still have our 50 states, but this is the average number of counties in each state, and here's our standard deviation. So we're going to, again, calculate and interpret the standardized score for Ohio. It tells us in our problem here that Ohio has 88 counties. It tells us that Ohio has 88 counties. So, Ohio has 88 counties, and in which distribution? Hang on, I think I'm... so Ohio has 88 counties, and then once we figure out the z-score here for the number of counties, then we're going to compare that to the number of representatives that they had. Okay, so our z-score for Ohio's number of counties. So we take Ohio's value of 88, and we subtract the mean of the number of counties, 62.82, and we divide by the standard deviation of 46.42. And we get a z-score of 0.542. So what that means is that Ohio is only half of a standard deviation above average in regards to the number of counties, but they are almost 75% above, or 75% of a standard deviation in regards to the number of representatives. So that means that Ohio is farther from the mean in the distribution of the number of representatives than they are in the distribution of number of counties. And that summarizes location in a distribution.